In this video, we're going to look at two examples. One balanced, where we're balancing a redox reaction in acid, and one where we're balancing it in base. I've purposely picked ones where we're going to have to worry about things like balancing oxygens and hydrogens. That way you have to worry about that. You've seen easier examples other places. So we'll look at two of these. So first, let's take this one. As a reminder, the first step we have to do is we've got to break this up into half reactions. So we've got to figure out, so I'm going to have my chromium species I have to balance, and then my iron species. I'd like to go ahead and do the easy one first. So in this case, Fe2 plus to Fe3 plus is fairly straightforward. As a half reaction, Fe2 plus reacting to form Fe3 plus. In this case, we can see we're changing from a 2 plus to a 3 plus state. That means the oxidation number has changed by 1 and it's gotten more positive. Since it's getting more positive, that means the species has to be losing electrons, so it has to be oxidized. And so that means the electron should go on the right side. Since I'm losing it, I'm giving it up from the Fe2 plus, and since this is a change of 1, it would be plus 1 electron. So as a half reaction on its own, it's just Fe2 plus goes to Fe3 plus an electron. We'll do some more balancing with that later once we've fixed the chromium and if we've got to change the number of electrons. So let's go and look at the chromium now. It'll be a bit more involved, but not too bad. So Cr2O7 2 minus in equilibrium with Cr3 plus. My suggestion is to do all of the atoms first and then worry about the number of electrons involved. So here we can see we've got chromium on one side and Cr2O7 2 minus. In this case, remember, that we're saying this is an acid. That implies that you have water around, right? So there will be water present, so it can show up in the reaction to balance the atoms, because right now the atoms aren't balanced. So first, chromium, there's 2 on the left, 1 on the right, so I need 2 chromium 3 pluses. Now to balance the oxygens, the species I have available to me are water that I can balance that with. So because there are 7 oxygens on the left, I'm going to add 7 waters on the right, because each water contains 1 oxygen. Now when I did that, I also added hydrogen atoms. Since this is an acidic set of acidic conditions, I'll have H plus available. So since I added 7 waters, that's 14 hydrogens, I can put 14 hydrogens on the left side. And now if you look, this reaction is now balanced. There are 14 hydrogens on each side, there are 7 oxygens, and there are 2 chromiums. Because we've done this, we now need to look at balancing our oxidation states to figure out where the electrons, whether they're reactants or products. It should be a reduction since the iron reaction is an oxidation, but we can check and make sure that's true. So our hydrogen is in a +1 state. Here, oxygen is -2. There are 7 of them. That makes that 14, a -14, but we want to get it to -2. To get from -14 to -2, you have to have a change of +12. Since there are 2 chromiums, that means you need a +6. Since +6 times 2 will give us +12. 12 minus 14 gives -2, which matches the charge of the polyatomic. Then over here, chromium's in a +3 state, since it's a monoatomic ion, keeps it like that. And our hydrogen over here is +1 and -2. So the species that changed was chromium. Chromium changed from a +6 to a +3 state. That means each chromium is gaining 3 electrons because it has to become less positive, aka more negative, and it's happening twice, so it needs to have 3 electrons 2 separate times. So we need to add 6 electrons in this case on our reactant side. So if we react 6 electrons with our ion here, it'll gain enough electrons to form 2 Cr3 pluses here. Now when we go to combine these reactions, the number of electrons exchanged should be the same. Electrons aren't just going to disappear or appear somewhere and then not go somewhere else. So our chromium reaction in this case needs to have 6 electrons available. So our iron reaction needs to provide 6. To do that, I can multiply by numbers. As long as I multiply by everything in the reaction by that number, the ratio stays the same. So if I need 6 electrons from my oxidation reaction to balance this, I would just multiply everything in that area by 6. Because if I have 6 iron 2 pluses that form 6 iron 3 pluses, I'll get 6 electrons out of the deal when I do that, since each one released 1 electron. And so now I can combine these 2 half reactions because the iron will release enough electrons for the chromium to absorb. So if I combine these 2 by adding them together, when I do that, I literally add them like an equation, and anything that occurs on the opposite sides of the reaction, like it's reactant one place, product in the other, cancels out. So in this case, our 6 electrons cancel out and nothing else does. So in the next question, we'll look at one where some stuff cancels, but this one, it's just the electrons. So this means our balanced equation is 14H plus Cr2O7 2 minus plus 6 Fe2 plus is in equilibrium with 6 Fe3 plus 2 Cr3 plus plus 7 waters. And this is our balanced chemical reaction. Note, by the ions, you could put AQ to make them aqueous, but this should be clear in the setup of these, that the ions are things that are aqueous, and the water is a liquid here. So that is our balanced reaction in acid. Because it's an acid, that means that you would expect to have hydrogen plus available as to participate in the reaction, so it's reasonable that there's 14 H pluses on our reactant side. Next, we'll look, though, at an example that's balanced in base, where we'd have to do one more step because it wouldn't make sense to have H plus readily available if you were in a basic environment. So let's look at that second example that's a little more involved. So here, we're going to balance SO32 minus plus MnO42 minus goes to SO42 minus plus Mn2 plus in base. The way I'm going to show you to balance this, I won't use the word basically, you solve this similarly to the acid condition. You just then add one more step at the end to get rid of all your H pluses and instead have OH minuses available, since you would expect there to be hydroxides, not H pluses present. So here, we start by balancing the half reactions just like we did with the others. So I'm going to take MnO42 minus is in equilibrium. Let me pause it. Okay, so we have MnO42 minus in equilibrium with Mn2 plus. So we'll do this half reaction first. So the manganeses are already balanced, so we just have to deal with the oxygens. So we do it the same way as before. We add waters to balance the oxygens. You do plus 4 H2O. And now I've added 8 hydrogens, so I'm going to start by putting 8 hydrogens over here. But I'm not going to end there, because I would not reasonably have 8 hydrogens available to me since I'm in a basic condition. I would expect there to be hydroxides. What we can do now, though, because the atoms are balanced, is I'm going to add hydroxides to both sides at the same time. Since adding hydroxides to both sides doesn't actually change the balance of atoms, because if I add an OH minus to the left side and to the right side, it's still balanced. And I'm going to add enough to neutralize all my H plus. So this will be 8 OH minus and 8 OH minus over here. I should have given myself a little bit more room. That's okay. So these are going to combine to form 8 water molecules, since an H plus and OH minus react. And so now I don't have any H plus to worry about. And I can now balance my waters. There's 4 on the right, 8 on the left. So these 4 would go away, and I would be left with 4 water molecules. Since if it's on both sides, it would be the same as if it didn't happen. If I reacted 8 waters to make 4, that's like there were just 4 added. So we now have a balanced reaction. 4 waters plus MnO42 minus reacts to form Mn2 plus 8 hydroxides. Now, I'm going to rewrite this equation and then account for the electrons, because we haven't dealt with the electron exchange yet, only with the atoms. This is an equilibrium with Mn2 plus 8OH minus. So if you check your atoms, these are balanced. We have, let's see, I have 8 oxygens on both sides, 8 hydrogen on both sides, 1 manganese. So I'm good with that. So if we set our oxidation states, our hydrogen and oxygen here are all going to end up the same. All the oxygens are -2. In this case, all the hydrogens are +1. So it has to be the manganese changing. On the right side, it's a +2. Over here, though, we have 4 oxygens at -2. That's an oxidation state of -8, but we expect to get to just 2 minus. So this has to be a +6, since +6 minus 8 gives you -2 to balance out, to make the oxidation state the same as the charge on the polyatomic ion. So we've gone from +6 to +2. That means we've become less positive, which means we have to gain electrons, and specifically we have to gain 4 of them. So that's going to leave 4 electrons on my left side here as one of my reactants. Now let's balance the other one. So now we have SO3 2 minus goes to SO4 2 minus. So here we have 1 difference in oxygen. The sulfurs are the same, so I'm going to have to add a water on the left. Then I need to balance the hydrogens, and so that's going to be 2 H pluses. And then I need to deal with the fact that I'm in base, so I shouldn't have H plus on its own, so I'm going to add 2 hydroxides over here, and I'm going to add 2 over here. When I do that, these combine to form 2 waters. From there, I can see I have 1 water over here, and so this 2 becomes a 1. So I now have a balanced equation. In terms of atoms, I have 2 hydroxides plus SO3 2 minus is at equilibrium with SO4 2 minus plus a water molecule. Now I need to deal with the fact that where my electrons are going to be. So my oxygens and hydrogens in this problem also are, all my oxygens are -2, all my hydrogens are +1 here when I sign oxidation rules. But let's figure out the sulfur. So here, oxygen's -2. There are 4 of them. That makes an oxidation state of -8. To get to -2 instead, this sulfur has to be +6. Since 6 minus 8 is -2, that matches the oxidation state of the charge on this polyatomic. Over here, oxygen's still -2, but now that's only 3 of them, so that's -6. So this sulfur is +4, since +4 minus 6 gets you to -2. From there, that means we're going from +4 to +6. We are losing 2 electrons since it's becoming more positive. I almost said more negative, more positive. So those electrons, since we're losing them, are products. So we have +2 electrons over here. Now, if I tried to combine the top and bottom reactions, the electrons wouldn't cancel out yet because there's 2 electrons on the bottom and 4 on the top. So I need to do the bottom reaction twice. So I need to double everything. So that'll be, I'm just going to rewrite it. So we have 4 OH minus plus 2 SO3, 2 minus, is in equilibrium with 2 SO4, 2 minus, plus 2 water molecules, plus 4 electrons. And then I'm going to rewrite the top equation so I can add them together. 4 electrons plus 4 waters plus MnO4, 2 minus, is in equilibrium with Mn2 plus 8 hydroxides. Now if I check, my 4 electrons cancel. I also see some of the other things cancel though too. So there's 4 waters on the left and 2 in the manganese reaction, and there's 2 in my sulfur-base reaction. So these 2 would cancel 2 of these waters since it's a reactant and product side separately. Then there's 4 hydroxides on the left of my sulfur containing reaction and 8 hydroxides on the product side of my manganese reaction. So these 4 hydroxides cancel 4 of the ones here to leave me with 4 present, since I don't need them to show up on both the reactant and product sides. When I go to add all these together, I'm going to write it to the right, but there's a little more room. I would get my reactants are 2 SO3, 2 minus, plus 2 water molecules, plus MnO4, 2 minus, is in equilibrium with, on the product side, 2 SO4, 2 minus, plus Mn2 plus 4 hydroxides. So that is my balanced chemical reaction of these 2 ions when they are present in base rather than acid. So hopefully those 2 examples help out some. They're a little bit more involved. They're still not too bad, right? It's just some steps to go through. How do you balance your atoms? How do you balance your oxygens? How do you balance your hydrogens? Then, once you've gotten that, figure out the electrons from the oxidation states. Make sure between both your half reactions they're the same number of electrons in both. If not, make a change to whichever one doesn't have as many, or if you need to change both of them. For example, let's say one lost 2, the other gained 3. Well, then you need to get them both up to 6. So just make changes to both equations where they have the same number of electrons being exchanged. Do that via multiplying by numbers to keep the ratios the same. So when I doubled this one, for example, for the sulfur components, that doubled everything, so the ratio stays identical, so that works out well. You can't just change the electrons and not anything else, or just some of the species. So with that, that systematic treatment should work for any problem you're going to work with, whether you're balancing an acid or base. Now, occasionally problems might not mention it. In those cases, there'll usually be problems where it doesn't matter, because some of them it doesn't change anything whether you are, and if it doesn't mention it and it does matter, then you can ask a question of me or figure out from context, is there some reason to think this should be an acidic or basic solution? Which should I have available? So hopefully that helps out.